Log on, tune in, find out. Another good idea from Cambridge.
From Cambridge, and she's talking about highly oscillatory integrals and their applications.
So I'm going to talk about highly oscillatory integrals and their applications. This is a PhD which I have done. Basically, this lecture is going to cover a PhD topic which I have done here in Cambridge with Arya Iserlis, and I want to take actually this opportunity to thank him for supervising it and for very exciting hot topic, and also to I would like to extend my thanks to everybody here because when I started my PhD it was the first HOP meeting here in 2006, and actually this PhD is basically outcome of similar workshops, so thanks everybody. Let's start about methods. I'm going to talk about a couple of methods which I explored during my PhD. It was the asymptotic expansion, which the truncated asymptotic expansion represented asymptotic method, the generalized Filon method, which was first developed, appeared in 1928 in a paper by Filon, right, if I'm right, and then the two godfathers of the generalized Filon are sitting here, Arya and Sivert, who developed the whole theory, and there was a number of PhD coming out of this theory. Magnus methods and Filon-Magnus method, which are the Magnus method will analyze certain time-dependent schemes, and Filon-Magnus method will analyze time-dependent schemes in presence of high oscillation. And for to solve nonlinearity, we introduce some iterative techniques, combination of waveform methods. I call it WRF, which means that iterative techniques, waveform methods combined with Filon quadrature. So a number of applications, as we know, has already, we heard already lots of lectures regarding these function approximations, spectral methods, modified Magnus Abel-Sutton address, oscillatory addition, PDEs is clearly Fourier analysis, harmonic analysis. There is a paper recently by Arya and Marisa also is sitting here in electronic engineering, I think, right, applications in that area, and also we are currently thinking with Dan in application in acoustics. So there is this is actually not even the whole list of possible applications. This is just to emphasize the importance of high oscillation and the wide range of applications that it appears. It's commonly known that the quadrature of highly oscillatory integrals was for a long time considered a problem of an overarching importance, and it was commonly considered also as a very difficult problem, and mainly most methods were based on taking very small step size to overcome this issue. So this lecture will present a couple of methods which basically present exactly the opposite, meaning that you can take as large step size as possible, and your accuracy of approximation will depend on the inverse powers of frequency, which means that you can take, basically you can have any order approximation, any desirable high order of approximation for large frequencies. As I said, the origin of the whole theory was first developed by Georges Napoleon Louis Filon in 1928, and later on this paper was, I think, discovered by Arya, and then they developed into a theory which I later developed the theory for the whole theory for solving ODEs, and now working on PDEs, also trying to extend those. So suppose f and g are smooth functions, and at the beginning we assume that g prime is not equal to 0 on the integral of Abbe, we look at the Fourier type integral for large frequencies. Omega here will be a real parameter, and increasing omega, of course, we consider large frequencies of oscillation of this integral. We know that the standard approach in classical theory will be based on Gaussian quadrature, which will choose extremely small step sizes to approximate this kind of integral. And the reason for this will be because the Gaussian quadrature, the approximation to this kind of integral, which has itself has order of 1 over omega, will be equal to big O 1, which means that if you approximate this integral by 0, it's even better rather than if you take Gaussian quadrature to approximate Fourier type integral for large frequencies. And this was shown in paper by Arié and Sievert in 2005. So how to obtain the asymptotic expansion? So it was suggested in the paper to integrate by parts. Integrating by parts, we first obtain the first element of the asymptotic expansion, which we denote by Q1A applied to F, and this is the remainder term. And presenting the following notation, we will just write the whole expansion for the integral in a very compact manner. So sigma 0 and sigma k plus 1 will be just those elements occurring each time from the integration by parts. So by definition, the truncated asymptotic expansion will represent asymptotic method which can be used already to approximate our oscillatory integral. And we can see that it already depends on the inverse powers of omega, which means that it depends on inverse powers of frequency, and that already suggests that your approximation will improve once you take large frequencies. And the following theorem, which is again theorem by Arié and Sievert, was stating that suppose that f and g are smooth functions and g prime is not equal to 0 on your interval of integration, then for large frequencies you can obtain the following asymptotic expansion, basically your asymptotic expansion for your integral, and your order of approximation by the asymptotic method will be 1 over omega to the power s plus 1. This is a very simple formula in case of gx equal to x, and this is actually very useful in application. This means that you need to evaluate this part only once, exponential. Basically, it means in applications to ODEs and later on in PDEs, this formula is very important because in this case, basically you will have here instead of this element, you will have a matrix. And this means that you will need to element this element only once. Here it won't appear. So from computational point of view, it becomes very cheap in future applications. So this is just to compare that we could have had this estimate from the van der Korput lemma, but at the same time we can see that asymptotic expansion offers much more terms. We can obtain much more terms from the asymptotic expansion, and it gives much more information rather than taking the estimate by the van der Korput lemma, which is a classical one. This one is stated by Stein. So, having obtained the asymptotic expansion, we would like to compare it with Taylor expansion, which is the classical expansion for analysis of most numerical ODEs. And we can see that in Taylor expansion, once you write the Taylor expansion for the function, if your y is oscillatory, here each time you will have to multiply h times frequency, which is exactly the reason why most classical methods fail in approximation of highly oscillatory ODEs. And we will exactly use the opposite. We will use methods which are based on the asymptotic expansion to make sure that our accuracy improves once the frequency grows. Basically, if the frequency will appear in the bottom, and our accuracy will depend on the inverse powers of the frequency. I would like to present the Filon type method next. Given the oscillatory integral IF, which is f of x times exponential to the I omega g of x for large frequency, we assume that there is no stationary points, though they can be still present, and the theory covers that part as well. We choose certain node points with multiplicities, and we construct a polynomial which will agree with our function values and derivatives at node points. And we construct the Filon type method, which by definition is the following: approximation of the function f by a polynomial f, and exponential will appear as a kernel here. And the following theorem will state that the asymptotic order of the Phelan type method is exactly the same as the asymptotic order of the asymptotic method, which basically means it will depend on the inverse powers of your frequency for large omega. And of course, this means that multiplicies at endpoints are larger, greater than equal to s. And this is very important point actually, because Phelan type method very much depends on the elements which on your function values and derivatives which will be approximated in the endpoints, because those are exactly the ones which will be cancelled in the asymptotic expansion. The asymptotic order of the Phelan type method won't improve if we increase the number of internal points. However, the accuracy of the Phelan type method will improve due to the fact that by doing so, you will decrease the constant in the leading term in your error. But that doesn't contribute to the higher asymptotic order. Here we take as an example g of x is equal to x, and omega changes from 100 to 200. And this is just an example which involves endpoints and first derivatives. This is the asymptotic method for IF, and this is the Phelan type method, just to show how simple formula looks like. And you can here notice that there is no truncation, no step size involved. We work with only endpoints. And we can see that the error for the Phelan type method will be 10 to the minus 8, for omega 10 to the, from 100 to 200, and for asymptotic method it would 10 to the minus 7. And this is again multiplicies or equal to 2. Omega changes from 100 to 200. Cosine x is instead of f, and g of x is equal to x, simply. So we can see that at the first instance, the asymptotic method had an advantage of having much more compact and simple formula, while Phelan quadrature has a slightly more complicated expression. But we, at the same time, we know that the asymptotic method blows up for small frequencies, while this is not the case for the Phelan type method. And it was shown in the paper by Arieh that for g of x is equal to x and small frequencies, the approximation by the Phelan quadrature is exact for polynomials of degree p minus 1. And this actually can be extended for, well, in general, the polynomial degree recovery in general is at least n minus 1 with the choice of right choice of the interval 3 quadrature weights. And this is also a very important result from the point of view of applications, because when you apply it to oscillatory ODEs and PDEs, the equation of large and small frequencies appears exactly there, and the question, does your quadrature cover all those issues? The answer is yes. Another advantage of the Phelan type method is that not only Phelan type method, there was a number of methods developing, including Levin type method by Hanover, is that it does not actually require derivatives by itself. One can consider sequence 1 over omega around 0 and 1 minus 1 over omega around 0.1, and both Phelan and asymptotic method use very little information, as we saw, to compute quite high accuracy, approximation with quite high accuracy. On this slide, I would like to show that if we do not include our endpoints in approximation with Phelan quadrature, we can see that the approximation will be of big O minus 1, which is the order of the integral itself, which again means that you do not do anything. There is no approximation basically happening here. So the endpoints are crucial in your approximation, and once you include them, you get the order of approximation 1 over omega square, and of course they will increase once we increase multiplicities of approximation of those points. A couple of slides which I'm not going to focus very much on, but just to say that the theory was developed even further, and the stationary points are also can also be allowed, and we can see that the approximation will be of big O big O omega to the minus 3 over 2, where we see that if G prime will vanish at certain points and nowhere else at 0, 1, while G double prime at psi k won't be equal to 0. So for certain k equal from 1 to r. So choosing those points among node points, we can see we will obtain the following order of approximation. From classical theory, we know that we could have one could argue that one can choose stationary phase method and apply for approximation, but we know that first it has to be integrates from minus infinity to infinity. This is a book by Olver from 1974. Or otherwise, it will require from F to have a compact support sufficiently near the stationary points of G. This is Stein, 1993. However, to relax those and to apply to our integral, we will denote the following generalized moments, and that will allow us to write our integral in the following representation, expecting that f and g are sufficiently smooth, and we know that there is a certain allowing certain stationary points. We know that g prime of psi is equal to 0, double prime is not equal to 0, and g is not equal to 0 at any other point, internal point in 0, 1. And the following lemma simply states simply represents the asymptotic expansion to our integral along stationary points. And this is similar notation as we had previously for sigma without stationary points. Even further, the asymptotic expansion can be extended for the case when g prime, g double prime up to certain r, they are equal to 0, and r plus 1 is not equal to 0 for certain r greater than equal to 1. And the following representation will be can be written for the integral if, which is the same Fourier type integral considered without this part of the lecture. And taking exactly the same representation, we can write the asymptotic expansion to if, allowing stationary points. And the following will be a much more general theorem which will state the asymptotic order allowing stationary points on the interval on your interval of integration. Basically, this is the asymptotic order with asymptotic method, basically applied to truncated asymptotic expansion. And similarly, the same result can be obtained for a Filon type method. Again, we take we make sure that our stationary points are among our node points, and we can construct a polynomial approximation, and thus the order will be exactly the same as before for the asymptotic method. Now, moving further, this was just an introduction to the classical, I call it already classical, what was developed many times ago for solving Fourier type integrals and stuff like that. So further on developing all this theory, it was developed for ODEs, and as I said, currently it is already a work of developing for PDEs. So in general, talking about high oscillation, one can in theory divide it into two parts, talking about intrinsic high oscillation and extrinsic high oscillation. One of it we consider is the one, intrinsic is the one which where oscillation is part of the inner nature of the underlying differential equation. That one example will be the area equation presented here. Another one, nonlinear example, will be Emden-Euler equation, the Hamiltonian system, and the famous Schrödinger equation. Those all will be part of the intrinsic oscillation. And for the extrinsic oscillation, which I just give an example, but I'm not going to consider this part. It was in a number of papers considered by Ari, actually. One can find is the extrinsic high oscillation is the one which originates in the force. The oscillation originates in the forcing term. This is one of the examples of such a system where omega is much larger than the norm of the matrix. Actually, here one can write exactly the asymptotic expansion for this kind of system, and we can see that the great advantage of using asymptotic expansion, suppose I truncate this expansion, and here you have any t basically I do not need to truncate this asymptotic I don't, well, of course I need to truncate it from the point of expansion, but I don't need to introduce any step size. So you can take any large t, substitute here, and just evaluate it, and you get very high accuracy to your approximation, to your integral. The following slide will present the family of highly oscillatory vector valued integrals, where we will consider the following product. X omega is a matrix valued kernel, and f is a vector valued function. X omega satisfies the following matrix ODE. Omega is still a parameter, and we assume that A is invertible and it has pure imaginary spectrum. So in this case, we will apply this. Once we solve that type of integral, we can apply that solution to solve systems of ODEs. For example, if we consider the following system, where again f is a smooth function, the same applied to conditions applied to the matrix A, and we know that using a variation of constant formula, we can write the solution in the following form. Here is the convolution, which is similar to the integral that I just represented, and if we can solve this one, then we can develop a numerical solution to our system. And we will start first from solving linear systems, and if I can manage, I will show also how to solve nonlinear systems and time dependency. So, applying similar techniques as before, we will integrate by parts and obtain the asymptotic expansion of the integral, which is already a matrix and vector valued function, basically. So integration by parts will give us first term of the asymptotic method, and continuing, we will obtain the following representation, which will define the asymptotic method. And as we can see, it will depend on the inverse powers of the matrix A, which also assumes that it will depend on the inverse powers of omega, in other words, frequency. The following lemma just states the asymptotic order, which is in L infinity norm, and also element-wise, we can see that it will depend on the inverse powers of the elements of the, well, approximation to the elements of A omega. And the corollary from this side is that which is very similar to the one which for the Fourier type integral, if f is f prime and up to certain s from 0 to s minus 1, if I is at A and B are equal to 0, then in L infinity norm, your integral itself has the following order, and element-wise, it has the following. The approximation has the following representation. And the corollary 2 states that if x omega is big O1 and f itself is big O1, then then the approximation itself is basically of the inverse powers of omega. And then yet another time, I would like to state that here that the asymptotic method does not depend on the step size, which means that again you can just truncate your asymptotic expansion and use it as a tool of approximation, and you do not need to basically, unless you have to basically program it numerically, which when you will have to take certain node points, but other than that, you can solve it symbolically just as well. And this is just to present how your approximation will look like. This numerical solver will look like once you substitute here the asymptotic approximation, and a couple of slides to show that if you take y double prime equal to minus omega times y minus cosine t with initial conditions 1, 0, and compare it with the exact solution, you can fix the step size 1 over 2 and start increasing your omega. You can see that for omega 10 you have 10 to the minus 2, omega squared 10 to the minus 4. You do not change your step size, you continue increasing your omega, you get 10 to the minus 6, 10 to the minus 8, and you compare this with Runge-Kutta method, you can see that it completely fails to approximate here for 10 to the power 2 already, and you compare it with MATLAB, you can see that for stiff ODEs, two solvers for stiff ODEs, you can see that it takes incredibly small step sizes with the following tolerance, and this is omega only 10 to the power 2. Well, you can make it to work slightly better, but for that it will take a very, very high cost, 10 to the minus 3, 10 to the minus 4 step size. Similarly, one can extend Filon type method for the same framework and approximate function f with a polynomial and construct the following approximation to the matrix and vector valued functions. And the following theorem simply states that it again, similarly to the classical theory, the asymptotic method for the Filon type method will be exactly the same as for the asymptotic method. And here is the scheme how to evaluate it with the Filon type method ODEs. A couple of numerical examples. Again, for a fixed step size, we increase frequency, and we can see that the equation and all the conditions are the same, and we can see we'll keep on increasing frequency for a fixed step size, and we get accuracy 10 to the minus 6, 10 to the minus 7, minus 8, and minus 10. And this is just the logarithmic error to show that what I just said was true. And I would like to say that this scheme can be applied for nonlinear systems as well. At each step, if we iterate and apply Filon quadrature, we can construct the following numerical scheme to solving nonlinear systems. And this is a theorem which will state the numerical order for if you discretize your integral with certain quadrature rule and apply your favorite waveform method, your numerical order will be the minimum of the bows, and thus it will be of order of your Filon quadrature if you apply Filon quadrature, because you will iterate until you get the order. And this is a table showing the dependency between step size and omega for the following nonlinear equation with initial conditions 1, 1. We can see that we can achieve accuracy 10 to the minus 10 almost for larger, but a little bit, here we have to pay a little bit higher price to take slightly smaller step size due to non-linearity of the equation. Now, at the next stage, I would like to show that the same ideas can be extended to solve oscillatory ODEs with time-dependent matrices. But the problem here is that you won't be able to integrate by parts straightforward, so you will have to apply certain trick. And this trick I will rather show on the example rather than in theory, because theory sounds a bit complicated. You will need to vectorize your matrix X omega to build from your original matrix A omega a new matrix which will take the A on diagonal, and to build from your original vector F the following matrix F. Now, once you multiply both, you will get the same basically vector. However, in this form, you can already apply integration by parts and obtain the asymptotic expansion, which means that you also need the following expression, which you can easily obtain from this information, the ODE, which will X prime will satisfy. And as a result, now you have the equivalent integral, and you can now integrate by parts and obtain the asymptotic expression for your integral, which is already time dependent. And the following is just a theorem stating the order, which taking into account that your B inverse is of order big O B hat, then here again you have inverse powers basically of your frequency, in other words, if you open the brackets. And similarly, you can extend the Filon type method, obtaining exactly the same asymptotic order for the Filon type method, and coming to the fact that okay, you can solve it, you can write it theoretically, but you have to solve the matrix exponential, and we know that it was shown by Magnus that the solution can be written in the following form, where omega t itself satisfies the following nonlinear ODE, And for example, if we truncate that expansion, then the sixth order Magnus method with Gaussian points will look as follows, where B can be obtained from the original matrix A. And a couple of numerical examples on the global error of the fourth order Magnus method for the area equation, and step size is 1/25. And also compared, this is compared with Hunke-Kutta method. We can see 10 to the minus 7 and nothing here. And this is the global error of the sixth order Magnus method for the area equation with the same initial conditions, step size 1/10 and 1/25 respectively. We can see 10 to the minus 4 and 10 to the minus 9. And the modified Magnus method will allow you to solve the equation, apply change of variables and to solve equation locally with a matrix with constant coefficients. And applying exactly Neumann expansion, as Arya said a couple of minutes ago, you can simplify your matrix and apply Filon quadrature. Once you simplify and apply Filon quadrature, you can see that this is exactly what you just said. You can take the truncate the Magnus expansion, compute integrals exactly, and then compute with Filon quadrature. You won't see any difference. It captures basically the whole accuracy. And this is with a step size 1/5, and a couple of more examples. This is global error of the modified Magnus method using Filon quadrature with endpoints, and multiplies again equal to throughout the paper. Step size is 1/2, and we can see time with on the time scale we took it almost up to 2000. We can see the difference here, 10 to the minus 7 we get. And the framework, the same. Now already you can build the Filon Magnus method, which will mean that you can solve your matrix exponential with Filon Magnus method and the whole integral with the Filon quadrature. And this is a couple of numerical examples already. We can see that for omega equal to the 10 to the power 2 and 10 to the power 3, already the frequency improves, and the equation is slightly similar to the area equation. It's minus omega t times y minus cosine t, initial condition 1, 0, and step size is equal to 1/4. And this is just to show that you can simply increase omega and get very nice accuracy of approximation up to 10 to the minus 11 here. And the step size, if you noticed, it wasn't very large. You can take even omega 10 to the power 5, well, slightly smaller step size, but still you can take h omega product. It's still 1000, which is not small at all. And this is the last slide to show that you can even compute omega 10 to the power 6 and get 10 to the minus 14 accuracy. So basically this is how you can solve the matrix exponential, and once you have solved the matrix exponential, the whole theory again is applied to solve nonlinear systems of ODEs with time-dependent matrices. And the whole theory, which I said at the beginning, you can allow stationary points, you can play with quadrature rules, and you can play with your favorite waveform techniques. Well, the theory will be the same, and it's just a framework where you can make the changes, your favorite changes, and build numerical methods for solving oscillatory ODEs. I stop here. Thank you.
Perhaps one short question before we get to the coffee. Everyone is exhausted. So let us reconvene at 4, and thanks again.